Hello, viewers. In today's session, we are going to discuss another important and conceptual problem from three-dimensional geometry. And in this session, we are going to discuss this problem where we are given the equations of two lines, and these two lines are given to be a perpendicular, right? So this is the first line, and we can take this line as L1. So the equation of L1 is x minus 1 over minus 3 equal to y minus 2 over minus 2k plus 1, and that is equal to z minus 3 over 3k. And the equation of the second line is given as x minus 1 over k minus 2 equal to y minus 2 over 2 equal to z minus 3 over 1, and let us call this line as L2. And these two lines L1 and L2 are given to be perpendicular, and we have to find the value of k. And then we have to also find the equation of the plane containing these two lines L1 and L2. So now if we compare the equations of these two lines with the symmetric form of the straight line in three dimensions, then we have x minus x1 over a y minus y1 over b and z minus z1 over c. So this is the symmetric form of the equation of a line in three dimensions, where x1 y1 z1 is the point through which the line passes, and here a b c are the direction ratios of the line. So if we compare this equation with this one, then this line L1, it passes through the point 1, 2 and 3. The value of x1 y1 z1 is 1, 2 and 3, and the direction ratios of the line L1 may be taken as A1, B1 and C1, and the direction ratios are given by minus 3, then we have minus 2k plus 1 and 3k, right? And if we compare this equation with this one, then this line also passes through the point 1, 2 and 3, and the direction ratios of this line L2 are given by A2, B2, C2, and here comparing these two equations, A2, B2, C2 are given by K minus 2, 2 and 1, right? So here these two lines L1 and L2 are given to be perpendicular, and we know that if two lines are perpendicular, then we have this condition, that is a1 b1 c1 dot, that is the dot product of these two direction ratios a2 b2 c2 is equal to 0, right? So we can also write it as a1 I cap plus b1 j cap plus c1 k cap, uh, and the dot product is taken with a2 I cap plus b2 j cap plus c2 k cap is equal to 0. So if the two lines L1 and L2 are perpendicular to each other, then the product of the dot product or the scalar product of the direction ratios of the two lines should be equal to 0, right? So here we have now by the definition of dot product of two vectors a1 a2 plus b1 b2 plus c1 c2 is equal to 0. So this is the condition for the perpendicularity of two lines L1 and L2. So now let us substitute the values of a1 b1 c1 a2 b2 c2 in this expression. So here we have a1 b1 c1 minus 3 minus 2k plus 1 3k, a2 b2 c2 is k minus 2 to 1. So we have now minus 3, then we have k minus 2, then we have minus 2k plus 1, and then we have 2, and then we have 3k, and here we have 1, and this is equal to 0. So let us now solve this equation for k. So we have minus 3k, then we have 6, then we have here minus 4k, then we have plus 2, then we have plus 3k is equal to 0. So now here we have minus 7k, minus 3k, minus 4k is minus 7k, plus 3k is minus 4k, and 6 plus 2 is equal to 8, and this is equal to 0. So we have minus 4k is equal to minus 8, k is minus 8 over minus 4, that is equal to 2, right? So the required value of k for which these two lines L1 and L2 are perpendicular is equal to 2, right? So the value of k is equal to 2. So now let us find out the equation of the plane containing these two lines, right? So let us now write the equations of the line L1 and L2 by taking k is equal to 2 in these two equations. So now if we take k is equal to 2 in the equation of line L1, then we have here x minus 1 over minus 3, y minus 2 over minus 2k plus 1. So taking k is equal to 2, over here we have minus 2 times 2 plus 1, that is minus 4 plus 1, that is minus 3. So here we have minus 3, and here we have z minus 3 over 3 times 2 is 6, and here in L2 we have x minus 1 over 2 minus 2, that is 0, and then we have y minus 2 over 2, and here z minus 3 over 1, right? So now the direction ratios of the line L1 are given by here minus 3, minus 3, and 6, right? And the direction ratios of the line L2 are given by 0, 2, and 1. And here we can see that the direction ratios of the line L1 are minus 3, minus 3, and 6. So if we divide these numbers by minus 3, then we have, so here we have 1, 1, and minus 2, right? Because we know that parallel lines have proportional direction ratios or equal direction ratios. So dividing these numbers by minus 3, we have 1, 1, and minus 2. So we can also write the direction ratios of this line L1 as 1, 1, and minus 2. So now let us draw a rough diagram here. Suppose this is the plane containing these two lines L1 and L2, and let us denote this plane by P, right? And here we have the line say L1, and here we have the line L2, right? And the normal vector to the plane P may be taken as n, right? So here we have the plane P whose equation is to be determined, and this plane P contains these two lines L1 and L2, and the vector n is the normal vector to this plane P, and this normal vector is perpendicular to both these lines L1 and L2, right? And see here L1 and L2 passes through this point, that is 1, 2, and 3. So here we can take this point 1, 2, 3, as x1, y1, and z1. So here the equation of the plane P can be given by this determinant equation. So the first row is given by x minus x1, y minus y1, z minus z1. The second row is given by the direction ratios of the line L1, that is A1, B1, C1, and the third row is given by the direction ratios of the line L2, that is A2, B2, and C2. So this is the equation of the plane P containing these two lines L1 and L2. The first row, it is x minus x1, y minus y1, z minus z1, where x1, y1, z1 is a point lying on the plane, right? And since these two lines lie on the plane P, so this point 1 comma 2 comma 3 may be taken as x1, y1, z1. The second row is the direction ratios of the line L1, and the third row is the direction ratios of the line L2. So now substituting the values we have now here, x minus 1, then we have y minus 2, z minus 3, and a1, b1, c1 are 1, 1, and minus 2, and a2, b2, c2 are 0, 2, and 1, right? So let us now expand this determinant of order 3 along the first row. So we have x minus 1, then we have here 1 times 1 is 1, then plus 4, then we have y minus 2, and then we have here 1 times 1 is 1, then here we have 0, and then we have z minus 3, and here we have 2 minus 0. So now we can simplify this expression. This is 5. 5 times x is 5x minus 5. Then we have here simply minus y and plus 2. And here we have 2z and minus 6, and that is equal to 0. So we have 5x minus y plus 2z, and here we have minus 5 plus 2 is minus 3, minus 3 and minus 6 is minus 9, right? So this is the required equation of the plane P uh, in the form that is ax plus by plus cz plus d is equal to 0, and the coefficients of x, y, and z gives us the direction ratios of the normal vector to this plane P. So the direction ratios of the normal vector are given by 5. Here we have minus 1, and then here we have 2, right? So the direction ratios of the normal vector to this plane P are given by 5 comma minus 1 comma 2. So viewers, this is how by using this equation we can easily find out the equation of the plane containing the two lines L1 and L2.